The news of NASA's near-light speed engine has taken the internet by storm. While its potential is captivating, many aviation enthusiasts are questioning its validity, if the engine truly defies the laws of physics as claimed. But the intrigue doesn't end there. What role does NASA play in developing this groundbreaking technology, and could it truly revolutionize space travel as we know it? Join us as we explore the details of NASA's newly designed near-light speed engine that might break the law of physics. Prior to the introduction of the speed engine, the M drive stirred up considerable debate in the realm of rocket science. Why? Because it seems to go against the fundamental laws of physics, the very things that make the universe tick. When British engineer Roger Scheuer first proposed the M drive, he described it as an engine that would use microwaves in a special cavity structure to create thrust, much like a light bulb, but with no moving parts and, crucially, no exhaust, no propellant, no problem. Physicist Stanislaw B. Shukalski, formerly with NASA's Glenn Research Center, and now at UFIT in Fort Lauderdale, believed it couldn't possibly work. This skepticism stems from a core law of physics, the conservation of momentum. Simply put, for an object to move in one direction, it must push something in the opposite direction. Conventional rockets follow this by firing hot gases backward. The M drive, however, claims to generate thrust without any such action, no messy expulsion of gases. Despite this fundamental challenge, Scheuer's idea began to gain traction. In 2006, he claimed that his prototype could produce 0.1 Newton of thrust, enough to gradually move a small satellite through space. This breakthrough caught the attention of NASA's EagleWorks lab, led by physicist Harold White. Now, NASA engineers at the Marshall Flight Center in Alabama have taken things even further, developing a revolutionary engine that doesn't rely on any propellant whatsoever. Even more astounding, this engine has the potential to reach the speed of light, defying the very laws of physics that rocket science has adhered to for centuries. Before diving into the concept of this near-light speed engine, let's first explore the M drive and what it truly represents. In 2013, Dr. Harold White and his team conducted a test on an M drive prototype. They reported detecting an incredibly tiny thrust. To put that into perspective, it's roughly equivalent to the weight of a single eyelash. While this force was minuscule, it was far greater than physics would predict based on known principles. Naturally, this sparked excitement within NASA. However, despite their attempts to clarify that this was a preliminary test and far from conclusive, the media ran with the story, spreading the narrative far and wide. The buzz extended globally. In 2016, Chinese space agency scientists revealed that they had been testing a similar device for 6 years and hinted at plans to conduct space tests. However, the notion of generating thrust by simply bouncing microwaves inside a sealed chamber raised concerns among physicists, dating back to the M drive's original introduction in 2006. By the time China announced potential space trials, their claims were riddled with so many inconsistencies that they seemed almost comical. Still, they maintained a serious tone. Despite setbacks, hope persists. The U.S. Defense Advanced Research Projects Agency continues to fund research into related concepts, such as quantum inertia. While the M drive remains highly controversial, it has ignited interest in other futuristic propulsion technologies, some of which have transitioned from science fiction to reality. One such breakthrough is the ion engine. The fascination with ion propulsion began with science fiction. Philip Nolan introduced the concept in his 1982 novel, Armageddon 2419 AD, and franchises like Star Wars later popularized it. But how do ion engines work in real life? Unlike traditional rockets that rely on combustion, ion engines operate by accelerating charged particles. They typically use xenon gas, which is fed into a chamber filled with electrons. These electrons collide with the gas atoms, knocking away electrons and turning the gas into positively charged ions. The ions are then accelerated through an electric field and ejected from the engine at extremely high speeds, creating thrust. This process is akin to letting go of an inflated balloon, propelling it forward as air escapes. However, there's a challenge. The ejected ions carry a positive charge, and if left unbalanced, the spacecraft would accumulate a charge so strong it could no longer maintain the electric field. To solve this, a neutralizer sprays electrons into the ion exhaust, ensuring the spacecraft remains electrically neutral. Ion engines might sound like something from a sci-fi movie, but they've been powering real spacecraft since the 1960s. NASA's first big success with this technology came in 1964 with the SURT-1 mission. Since then, ion engines have advanced a lot, becoming a key tool for exploring space. What makes ion engines special? They're incredibly efficient, able to speed up ions nearly 10 times faster than traditional rockets. Some modern ion engines can increase a spacecraft's speed by 25 miles per second, a massive boost during a mission. However, they don't produce much thrust, generating only enough force to keep a piece of paper from floating away. That might sound weak, but once a spacecraft is in space, these engines shine, steadily pushing it to far-off destinations more efficiently than chemical rockets. Despite their slow acceleration, ion engines are perfect for long space missions. NASA's Dawn spacecraft, for instance, used ion engines to do something no other spacecraft had ever done: orbit 2 different asteroids. The European Space Agency's Bepi-Colombo mission is also using ion propulsion for its 7-year journey to Mercury. Even Elon Musk's SpaceX employs ion engines in its Starlink satellites for precise maneuvers in orbit. The roots of ion engines go back to 1917, when American physicist Robert Goddard explored new ideas for propulsion. Goddard is often called the father of modern rocketry, and while he didn't directly work on ion propulsion, his concepts inspired future researchers. The first working ion engine was built in 1959, and just a few years later, NASA tested it in space during the SURT-1 mission. For 31 minutes, the engine worked in the harsh environment of outer space, proving ions could propel a spacecraft. Around the same time, the Soviet Union developed its own ion engine called the plasma erosion engine. Soviet scientists continued refining their designs, eventually creating engines like the SPT-25, which became widely used on Soviet spacecraft by the 1980s. While the United States slowed its progress on ion engines in the 1970s due to budget cuts, interest revived in the 1990s as NASA planned ambitious deep space missions. One of the most famous missions using ion propulsion was NASA's Deep Space 1, launched in 1998. It was the first spacecraft to rely entirely on an ion engine, proving the technology's reliability for long-haul journeys. Other countries also joined the ion propulsion race. Japan's Hayabusa mission, launched in 2003, used ion engines to land on an asteroid, collect samples, and bring them back to Earth, a groundbreaking achievement. Ion engines have come a long way, transforming from experimental technology into the driving force behind some of humanity's most ambitious space missions. They work by providing gentle but constant thrust, enabling spacecraft to travel farther and faster than ever before. Whether it's reaching distant asteroids, orbiting dwarf planets, or powering satellites closer to Earth, ion engines are revolutionizing how we explore the universe. From their humble beginnings to their role in today's space missions, these engines are a testament to how patience and innovation can push the boundaries of what's possible. Ion engines have gone from experimental ideas to critical tools for space exploration, making some of the most ambitious missions possible. These engines are unique because they deliver constant, gentle thrust over long periods, enabling spacecraft to achieve incredible speeds and travel to far-off destinations. One of the first breakthroughs came in 1998 with NASA's Deep Space 1. This mission proved that ion propulsion could work reliably in deep space. The engine ran for an astounding 16,250 hours, far exceeding expectations and setting the stage for future projects. It was a major leap forward, showing the world what ion engines could do. The European Space Agency took the technology closer to home with the 2009 launch of the GO-C satellite. Using an ion engine, GO-C maintained an exceptionally low orbit, just 225 kilometers above Earth. This allowed it to make some of the most precise measurements of Earth's gravity ever recorded, proving ion engines weren't just for deep space. In 2003, ESA's SMART-1 spacecraft showed how ion engines could even be used for lunar missions. The probe spiraled out from Earth and successfully orbited the Moon, marking another milestone. Meanwhile, Japan's Hayabusa mission, which was also launched in 2003, relied on ion propulsion to visit the asteroid Itokawa, collect samples, and return them to Earth, a historic first. Hayabusa's engines ran for nearly 40,000 hours during its journey. NASA's Dawn mission in 2007 took ion propulsion to the next level. It became the first spacecraft to orbit two extraterrestrial objects, the asteroid Vesta and the dwarf planet Ceres. Over its mission, Dawn's ion engines changed its speed by an incredible 11 kilometers per second, a feat that would have been impossible with traditional chemical rockets. Ion propulsion isn't just for exploring distant worlds. It's shaping modern satellite technology too. SpaceX's Starlink satellites, designed to provide global internet, use ion thrusters to fine-tune their orbits and avoid collisions. This technology helps keep the satellites precisely positioned while extending their operational lifespans. But ion engines are only one piece of the puzzle in humanity's quest to explore space. Enter nuclear thermal propulsion, an idea first explored in the 1950s, but now seeing renewed interest. Unlike ion engines, NTP uses a nuclear reactor to heat hydrogen fuel to extreme temperatures. This creates powerful thrust, potentially making space travel twice as efficient as today's chemical rockets. With NTP, spacecraft could carry less fuel and more equipment or supplies. Missions to Mars could be completed in nearly half the time, reducing risks for astronauts. This technology could even open the door to exploring the outer planets and their moons, such as Europa or Enceladus. Countries like the US, Russia, and China are racing to make NTP a reality. NASA and DARPA's Draco program aims to test a nuclear engine in space by 2025, while Russia and China have their own ambitious plans. Safety and public perception remain challenges, but the potential rewards, faster, more efficient space travel, are too great to ignore. As humans push the boundaries of space exploration, ion engines and NTP represent two of the most exciting advancements. Whether it's precise satellite positioning, asteroid missions, or the dream of reaching Mars, these technologies are driving us closer to the stars. Let's move on to this near-light speed engine that seemingly defies the laws of physics. Traveling at the speed of light might sound like something out of a sci-fi movie, but it's not as far-fetched as you might think. For perspective, light zips through space at a mind-blowing 299 million meters per second. That's incredibly fast, so fast that many believe it's beyond human reach. Yet history has shown us that the word impossible rarely stops us. NASA's latest invention might just be the next step in breaking barriers and exploring the unknown. Think back to 1947, breaking the sound barrier was once thought to be impossible too. Then came the Concorde, a jet so fast it cut the New York to London trip to under 3 hours by flying at twice the speed of sound. Though these jets aren't around anymore, they prove that once unimaginable feats can become reality. Similarly, the idea of traveling near the speed of light might seem crazy today, but history tells us not to bet against human ingenuity. Space travel, as it stands, faces a massive challenge: distance. Even the closest stars are so far away that it would take thousands or even millions of years to reach them with our current technology. Imagine trying to get to Alpha Centauri, the closest star system, using today's fastest spacecraft. NASA's New Horizons, which zoomed to Pluto at an astonishing 58,000 kilometers per hour, would still need 78,000 years to reach it. And that's not even considering the fuel it would need for such a journey. This is where NASA's new groundbreaking idea comes in. David Burns, a NASA engineer, has proposed a revolutionary new spacecraft engine that could potentially travel at 99% of the speed of light. What makes this concept even more astonishing is that it doesn't rely on traditional rocket fuel. Called the helical engine, this innovative design uses a clever method of acceleration that could change the future of space exploration forever. If Burns' engine becomes a reality, it could revolutionize how we think about space travel. Instead of taking lifetimes to explore distant stars, we could shrink those journeys to manageable timeframes, opening up the universe in ways we've only dreamed of. With this kind of technology, finding new planets, or even visiting them, might not just be science fiction anymore. It could be the next giant leap for humanity. Now, NASA engineer David Burns has proposed an even wilder idea: the helical engine, which might change how we think about space travel forever. So how does this futuristic engine work? It cleverly uses a strange feature of Einstein's theory of relativity. Instead of burning fuel and shooting exhaust out the back, it speeds up a loop of ions, tiny charged particles, until they're almost as fast as light. Here's where it gets interesting. As the ions move faster, their mass increases. This extra mass creates enough force to push the spacecraft forward without anything being expelled. It's almost like a physics magic trick. Imagine putting a spring-loaded ring inside a box. Normally, when the ring bounces around, the box barely moves. But if that ring were moving at near light speed, something incredible happens. Its mass grows, and when it hits the ends of the box, it pushes it forward. That's the basic idea behind Burns's engine. It takes advantage of this mass-changing effect to generate thrust in a completely new way. What makes the helical engine so exciting is that it doesn't need traditional fuel. Rockets today burn tons of propellant, which limits how far they can go. But Burns's engine uses an ion accelerator to create movement, meaning a spacecraft could, in theory, keep going indefinitely. This could open the door to exploring places like Alpha Centauri, the closest star system to Earth, at speeds we once thought were impossible. Of course, this idea is still in its early stages. While Burns's concept has sparked excitement in the scientific community, it's also drawn criticism. Some experts argue that the engine seems to defy known physics and might not work in the real world. Others compare the buzz around this concept to the hype surrounding the controversial EM drive, which many believe was too good to be true. Even so, Burns's helical engine is a fascinating glimpse into the future of space travel. If it turns out to be viable, it could revolutionize how humans explore the universe, making trips to distant stars faster and more practical. It's an exciting idea that pushes the boundaries of science and imagination. And who knows? It just might change everything. The helical engine, much like the EM drive, remains a concept that has yet to prove itself. Both ideas face a major challenge. They seem to break the law of conservation of momentum, which says that a system's momentum stays constant unless an external force acts on it. In simpler terms, if the helical engine could work, it would defy what we currently understand about physics. But here's the twist. It's based on Einstein's special relativity. This theory says that as objects move closer to the speed of light, they gain mass. Dr. Burns, the engine's creator, suggests a bold idea. Instead of a traditional design, the helical engine would use a coil-shaped accelerator to move ions in a loop. By speeding these ions up to nearly the speed of light and changing their velocity, the engine could theoretically create thrust without ejecting any fuel. Electric and magnetic fields would control everything, and it would operate in a vacuum without moving parts. It sounds like science fiction. However, there are big hurdles to overcome. For starters, the engine hasn't been tested, and many experts doubt it will ever work. If it does, it could challenge some of the most basic principles of physics, or perhaps expand our understanding of them. Even so, there are practical problems. The engine would need to be massive, around 200 meters long and 12 meters wide, to function. It would also require a staggering 165 megawatts of power to produce just a tiny amount of thrust, making it extremely inefficient. Another limitation is that the helical engine can only operate in the frictionless environment of space. Dr. Burns claims it could theoretically reach 99% of the speed of light if given enough time and power. This speed would let astronauts reach Mars in just 13 minutes, or the Moon in a little over a second. However, the current design remains purely theoretical, and we're far from seeing it in action. Despite these challenges, the idea is exciting. Unlike conventional rockets, the helical engine wouldn't need fuel, making it a game-changer for long-term satellite operations or deep space exploration. Even though it's just a concept for now, it opens doors to new possibilities and sparks hope for faster space travel. Will the helical engine take us closer to the dream of light-speed travel? Only time and innovation will tell. But with ideas like this pushing the boundaries of what we know, the future of space exploration seems brighter than ever. Forget about having the largest army. Today's warfare is about speed. American paratroopers are boarding huge C-17 planes that can quickly transport troops and tanks to any crisis area around the world in just a few hours. This represents a completely new approach to fighting, and the United States is at the forefront. How is the United States military adapting technologies to win battles in hot military zones? What capabilities does the C-17 have that have given their Air Force an advantage over others? Join us as we take a look at the next-generation aircraft ready to take on powers like Russia and China. When you see a lot of American paratroopers piling into C-17 planes at the same time, it usually means one of two things. First, they are about to start a large military operation. Or second, it's a big training exercise. They do these to demonstrate how quickly they can move a group of troops from one place to another. The C-17 is their go-to vehicle for situations like this. That's because it can carry a lot of weight, whether it's heavy equipment or a full load of soldiers. Plus, it's pretty impressive when it comes to distance. It can transport a lot of gear and troops over long distances. The C-17 Globemaster III is America's workhorse in the sky. Before the C-17, Boeing tested a smaller plane called the YC-15 in the 70s. The Air Force wanted something to take over from their older cargo planes, the C-141. So they took that YC-15 design and made it bigger, changed the wings, and added stronger engines. But getting it right wasn't easy. Boeing lost nearly $1.5 billion just trying to perfect the design. The aircraft does a bit of everything, flying troops and supplies around the world, helping with medical emergencies, and even dropping cargo from the sky. In the 1970s, the Air Force needed to replace their aging C-130 cargo planes, so they held a contest between two companies, Boeing and McDonnell. Boeing showed up with the YC-14, while McDonnell Douglas brought their YC-15. Both planes did better than expected, but the Air Force canceled the competition before picking a winner. However, in 1979, they changed their minds because they wanted an even bigger plane that could fly longer distances. McDonnell Douglas decided to improve their earlier YC-15 design, and Boeing offered a bigger version of their YC-14 with 3 engines. Lockheed also pitched 2 ideas based on their existing planes, and in August 1981, the Air Force picked McDonnell Douglas's C-17 design. The new plane was much bigger than the old YC-15, with slanted wings and stronger engines. It could do everything the old C-141 did, plus some jobs usually handled by the massive C-5 Galaxy. This meant the C-5s could focus on moving the biggest cargo. While waiting to build the C-17, the Air Force looked at other options. They thought about making their C-141s bigger, buying more C-5s, getting extra KC-10s, and using more civilian planes when needed. But money was tight, so they had to wait 4 years. During this delay, they didn't sit still. They paid companies to work on the design and test the engines. By December 1985, they were finally ready to start full development under program boss Bob Klepper. The plan was to fly the first plane by 1990, and 210 of these planes were ordered. The late 80s brought more headaches. Design problems and budget cuts kept delaying the project. Critics questioned whether the plane was worth the money and suggested cheaper options. By April 1990, they cut down the order to 120. The first C-17 finally took off in September 1991 from Long Beach, California, about a year late. However, the C-17 hit serious trouble in 1992 when its wing broke during testing, and fixing the wings cost $100 million. When they tested again in September 1993, the wing broke again. Later on, the engineers found out that they had made a mistake during the test and that the wing was strong enough. In early 1993, they officially named it the Globemaster III. But by year's end, things looked grim. The Defense Department gave McDonnell Douglas 2 years to fix their production problems and cost overruns, or they'd cancel the contract after just 40 planes. Taking this deal cost the company nearly $1.5 billion in losses. In March 1994, the military looked for cheaper ways to get the cargo planes they needed. They thought about buying modified Boeing 747 jumbo jets, making more C-5s, keeping their old C-141s flying longer, or sticking with the C-17. They narrowed it down to 3 choices: a special Boeing 747, which they would call the C-33, an upgraded C-5, or more C-17s. All this happened because they had capped C-17 orders at 40 planes back in December 1993 to check if they could get better value elsewhere. By April 1994, The C-17 was still in trouble. It cost too much, was too heavy, burned too much fuel, and couldn't carry enough cargo far enough. The test pilots found problems with its computer systems, landing gear, and other parts. Things got so bad that in May they talked about building only 32 planes. That idea got dropped, but the headaches weren't over. In July, government watchdogs found a big problem with earlier studies. The Air Force had claimed the C-17 could land at 6,400 more runways worldwide than the bigger C-5. But they had only looked at runway size, not how much weight the runways could handle. When they counted both, the C-17's advantage dropped to 911 runways. The C-17 also struggled with airflow problems during drop tests. By February 1997, they found another issue. A fully loaded C-17 needed much more runway space than planned, especially on wet surfaces. As American tanks and vehicles got bigger over the years, the Air Force needed a plane that could handle the massive loads, even ones too awkward to fit on standard cargo pallets. After the remodeling, all the problems were fixed and the Air Force got value for their investment. The C-17 aircraft is 174 feet long, with wings spanning nearly 170 feet. Its special wing design, angled slightly downward, helps keep it steady in flight. The tail sits high like a T, making the plane more stable and cutting down on air drag. It runs on 4 massive engines made by Pratt & Whitney, similar to what you would find on a Boeing 757 passenger jet. These engines have a clever feature. They can blow their exhaust up and forward, which helps the plane back up without sucking debris into the engines. Pilots can even use this in flight to help them descend faster. When 2 C-17s fly in formation, with one riding the air currents from the other, they can save up to 10% on fuel. The C-17 needs 3 crew members to move cargo: a pilot, co-pilot, and loadmaster. Inside, the cargo hold is 88 feet long, 18 feet wide, and 12 feet high. The floor has a neat trick. One side has rollers for sliding cargo containers. But flip it over, and it's flat for rolling vehicles. Everything loads through a huge back ramp that is big enough to swallow a 69-ton Abrams tank, plus trucks, other armored vehicles, or standard cargo loads. The aircraft can lift 170,000 pounds of cargo even when it is fully loaded with fuel. It weighs in at 585,000 pounds, load it with 160,000 pounds of cargo, and it can fly about 2,400 miles without refueling. Newer models can go even further, 2,800 miles, thanks to an extra fuel tank in the wing. The plane cruises at 450 knots or about 830 miles per hour. It can carry 102 paratroopers with all their gear, and when flying empty, it can travel over 6,000 miles. The C-17 can land on runways just 3,500 feet long and 90 feet wide, much smaller than typical military airfields. It can even handle dirt runways in a pinch, though that risks damaging the plane, and thanks to its reversible engines, it can back up and turn around on narrow taxiways. The plane is built to be reliable, needing only 20 hours of maintenance for every hour of flight, and stays ready for action 74% of the time. The first C-17 touched down at Charleston Air Force Base in South Carolina in July 1993. By January 1995, the 17th Airlift Squadron was up and running with the new plane. It broke 22 records for carrying massive loads and even won the Collier Trophy in 1994. In 2006, 8 C-17s found a new home at March Air Base in California. These were split between Air Force Reserve units. Later, some moved to Dover Air Base in Delaware to work alongside the bigger C-5 planes. That same year, Mississippi's Air National Guard got their first batch of 8 C-17s. By 2011, New York's Air Guard switched from C-5s to C-17s. The C-17 flew military supplies to troops in Afghanistan and Iraq, and rushed aid to Haiti after the 2010 earthquake, and then to Pakistan during the 2011 floods, bringing food, medicine, and emergency gear. One of its biggest missions came in March 2003, when 15 C-17s dropped 1,000 paratroopers into Iraq, the largest combat drop since Panama in 1989. After that, they kept moving tanks, fighting vehicles, and artillery to the battlefield. The plane helped America's allies too. It carried Canadian vehicles to Afghanistan in 2003 and moved Australian troops to East Timor in 2006. That same year, these planes hauled 15 Canadian tanks from Kyrgyzstan to Kandahar for NATO. By 2013, American C-17s were helping French forces in Mali, working alongside British, NATO, and Canadian planes. Pilots have a funny nickname for the C-17. They call it the Moose because its fuel vents sound like a female moose. Since 1999, these planes have been flying to Antarctica yearly to support American research, taking over from the older C-141s. The crews made the first flight from the 62nd Airlift Wing. Each October, they fly between New Zealand and McMurdo Station, a 5-hour trip each way, and started dropping supplies from the air in 2006, delivering 70,000 pounds in their first drop. The C-17 also serves as part of the presidential fleet, which is really interesting. When the president travels, the aircraft carries his armored limo, helicopter, and security teams. Sometimes it even flies the president himself. When it does, it uses the famous Air Force One call sign. In 2015, C-17s helped test America's missile defense by launching fake missiles at Wake Island. The targets helped test both land and ship defense systems. Then, in early 2020, they tried something new, dropping special pallets loaded with weapons from C-17s and C-130s. The Air Force liked what they saw. On August 15, 21, things were chaotic at the Kabul airport in Afghanistan. The Taliban was taking over the city, and a lot of people were desperate to get out. In the middle of all this, a United States Air Force C-17 cargo plane took off from the airport. Can you believe it? There were people holding onto the outside of the aircraft as it flew away. Sadly, at least 2 of them ended up falling to their doom. But that was not the only crazy flight that day. Another C-17 managed to cram 823 Afghan evacuees on board. That's an insane number of people for one plane. The previous record was around 670 during a typhoon evacuation in the Philippines back in 2013. Goes to show how dire and urgent the situation was in Kabul for so many to pile into that aircraft. Can't imagine what it must have been like for the people on board and the crew. An unforgettable and harrowing experience, to say the least. Boeing wanted to sell the C-17 to countries in Europe, like Belgium, Germany, France, Italy, Spain, and the United Kingdom. The United Kingdom's Royal Air Force wanted to be able to work closely with the United States Air Force and share some weapons and capabilities. Back in 1998, they realized they needed a big strategic cargo plane, and they started looking at options in September of that year. But by August 1999, they canceled the bidding process. Some options, like the Boeing and British Aerospace C-17 offer, were just way too pricey, and the others were not quite right for what they needed. But the C-17 was still the top pick. Then in May 2000, the United Kingdom's Secretary of Defense, Jeff Hoon, said that because the Airbus A400M plane was delayed, they were going to lease 4 C-17s from Boeing instead, and that it would cost 100 million euros per year for the first 7 years, with an option to extend the lease for 2 more years after that. The UK could either choose to buy the planes outright or give them back to Boeing at the end of the lease. The catch was that the United Kingdom promised to upgrade their C-17s like the US Air Force did. That way, if they gave the planes back, the United States could easily take them into their fleet. But there were also limits on how the UK could use the leased C-17s. No parachute drops, no airdrops, no rough landings, no low-level flying, and no air-to-air refueling. So it wasn't a completely free deal, but it got them the big cargo carriers it needed. The Royal Air Force got its first C-17 on May 17, 2001. It was handed over at Boeing's facility in Long Beach and then flown to RAF Bryce Norton by a crew from 99 Squadron. They got their 4th C-17 a few months later on August 24, 2001. The British planes were some of the earliest to have a new, bigger fuel tank in the middle of the wing. In the Royal Air Force, the C-17 did not have a fancy official name. No Hercules or anything like that. They just call it the C-17, or sometimes the C-17 a Globemaster. Initially, the C-17 was supposed to be a backup in case the A400M plane did not work out. But the plans changed when the Ministry of Defense said they were going to buy the 4 C-17s they leased, even though by then the A400M seemed to be getting closer to being ready. The thing is, the C-17 gave them some major capabilities that they really did not want to lose, like being able to carry way more cargo, 169,500 pounds, versus the A400M's 82,000 pounds. That's a big difference. Plus, they can use the C-17 as a flying hospital to evacuate people for medical reasons. It's a super useful and versatile aircraft for them. So in the end, they decided it was better to just keep the C-17s they had rather than take a chance on the new A400M. There are different variations of the C-17 aircraft. First off, you've got the basic C-17A. That's the original military transport version. Nothing too fancy, but it gets the job done. Then there's the C-17AER. That stands for Extended Range. It is not the official name, but everyone calls it that because it can fly further thanks to an extra fuel tank in the middle of the wing. They started adding that feature in 2001 with the Block 13 planes. Speaking of blocks, Block 16 was a big upgrade. It had better software and hardware, like an improved oxygen system, a new weather radar, and some other tweaks to make it fly smoother. The latest and greatest is Block 21. It's got all the bells and whistles, a better navigation system, a new way to identify itself to other planes and air traffic control, and some slick updates to the communication gear and flight computer. There were also other variants, but these ones never saw the light of day. For instance, the C-17B was supposed to be a souped-up tactical airlifter. The idea was to throw an extra landing gear under the belly and beef up the engines. Why? So it could land and take off in shorter distances. Boeing tried to sell this to the US military back in 2007. They pitched it as the perfect ride for hauling around the Army's future combat systems vehicles and gear. Next, there was the KC-17. Pretty straightforward. It was going to be a flying gas station, a tanker version of the C-17. Then you had the MD-17. This was the version Boeing cooked up for the airlines taking part in the Civil Reserve Air Fleet. But after Boeing and McDonnell Douglas tied the knot in 1997, they changed the name to BC-17X. So yeah, that's the rundown on the different C-17 variants. The names and details might seem like alphabet lines, but at the end of the day, they are all just big super cargo planes that give the United States an advantage over others. The greatest threats are the once unseen. Beneath the ocean, Israel's INS Drakon and the United States Virginia-class submarines are moving silently, armed with cutting-edge technology and firepower that could alter the course of a conflict in an instant. Together, they are rewriting the rules of naval warfare, stealthier, deadlier, and ready to strike before you even know they're there. How do they stay hidden? What makes them so deadly, and what does their presence mean for the future of naval warfare? Join us as we uncover the secrets of the silent force shaping the seas. The Dolphin-class submarines were designed in Israel but built in Kiel for Israel's Shayetet 7 naval unit. The first submarines were based on Germany's Type 209 export model, but were made bigger with some changes. The Dolphin 1 submarines are a bit larger than the German Navy's Type 212 in both length and weight. The three newer submarines have powerful technology that lets them stay underwater as long as Type 212 submarines. However, they are 12 meters, which means they are about 39 feet longer and weigh about 500 tons more when they are underwater. What this translates to is that they would need more crew members than both the Type 212 and Type 214 submarines. Germany has not built any submarines this big since the Second World War, so these are also the most expensive vehicles in Israel's military. Israel bought these Dolphin submarines to replace their old GAL submarines, which they have been using since the late 1970s. Each Dolphin submarine can carry up to 16 weapons total, which is a mix of torpedoes and Popeye turbo cruise missiles. And these missiles can travel at least 1,500 kilometers. Several sources suggest they might even carry nuclear warheads with 6 kilograms, which is approximately 13 pounds of plutonium, giving Israel the ability to launch nuclear weapons from submarines. However, this nuclear capability has not been officially confirmed. Israel first planned to buy these submarines in the year 1989. They, however, ordered them in January 1990, but had to cancel the order by November. They needed the money to defend against Iraq's threats during the buildup to the 1991 Gulf War after Iraq took over Kuwait. Later, Germany helped restart the project by paying the full cost of the first two submarines, the Dolphin and Leviathan, and also paid half the cost of the third one, named Takuma. During the First Gulf War, it came out that German companies had helped Iraq improve its missiles and chemical weapons. This happened even though West Germany had agreed not to do this in 1987. The improved missiles could now reach Israeli cities. And although Israel was not fighting in the Gulf War, Iraq still fired these missiles at Israeli cities. To make up for damage to Israel during the war and to keep German shipyards working during defense budget cuts after the Cold War, German Chancellor Helmut Kohl agreed to help German companies build two Dolphin submarines for Israel. Israel named the first two submarines after the old British submarines they used in World War II. The third one, Takuma, which means revival, honors the Dakar, an Israeli submarine that sank in the Mediterranean in 1968 with its entire crew. In 2006, Israel ordered two more submarines from ThyssenKrupp's HDW shipyard. These new versions were 28% heavier than the older Dolphins and had special AIP engines like the German Type 212 submarines. Germany agreed to help pay for the start of construction with 170 million euros, with plans to deliver the submarines in 2012. The two submarines cost about 1.3 billion euros in total, with Germany paying up to one-third. In 2010, both countries said they weren't discussing a sixth submarine. But the following year, Israel ordered one anyway, reportedly for $1 billion without German help. Things changed that July when German Defense Minister Thomas de Maizière met with Israeli Prime Minister Netanyahu and Defense Minister Barak. They agreed Germany would pay 135 million euros of the $500 to $700 million cost. In late 2016, reports came out about talks to buy three more submarines from ThyssenKrupp. This led to controversy when former Defense Minister Moshe Ya'alon, who had opposed buying the submarines, asked Attorney General Avichai Menablit to look into the deal. Ya'alon was concerned because Prime Minister Netanyahu's lawyer, David Shimron, was working with Mickey Ganner, who represented ThyssenKrupp in Israel. On November 23, 2016, Mandelblit decided to have prosecutors investigate the case. In July 2021, after Netanyahu's government lost power, new Defense Minister Gantz and MK Saar started looking into the submarine deal more seriously. They called it the Case 3000 and said they needed to investigate every part of how the submarines were purchased. In October 2017, Israel and Germany agreed to a deal for three more Dolphin submarines, to be delivered starting in 2027. They officially signed the agreement in January 2022, planning to get the first submarine within 9 years. These new submarines would replace the first three Dolphins, which would be about 30 years old by then. Germany agreed to help pay for a third of the cost by supporting German companies in building the submarines. The two submarines have 10 torpedo tubes, 6 that are 533 millimeters, which is 21 inches wide, and 4 larger ones that are 650 millimeters, or 26 inches wide. The bigger tubes can be used for mines, large cruise missiles, or small vehicles that carry divers. These tubes can also fire regular torpedoes and missiles if special liners are added. The submarines first used Atlas Electronic DM-2A3 torpedoes that could be guided by wire. These torpedoes carried a 260-kilogram warhead and could work in two ways. When actively tracking targets, they could go 40 knots, that is 74 kilometers per hour and 46 miles per hour, and hit targets 13 kilometers, 8.1 miles away. In passive mode, they moved slower at 22 knots, but could reach 28 kilometers at 17 miles. Israel later got newer DM-2A4 torpedoes to replace the older ones. These use electric power and fiber optic cables to communicate, which made them better at avoiding enemy defenses thanks to improved electronics. Military experts think Israel's Dolphin submarines can carry nuclear weapons, giving them a backup way to launch them from the sea. When Israel tried to buy long-range Tomahawk missiles in 2000, the United States did not agree to this purchase due to international rules, however. Its own Navy used its submarine torpedo tubes to launch both nuclear and regular Tomahawk missiles. Two major research groups, the Federation of American Scientists and GlobalSecurity.org, say the submarine's larger torpedo tubes can fire Popeye turbo cruise missiles that might carry nuclear weapons, and that the United States Navy saw Israel test one of these submarine missiles in the Indian Ocean and the submarine missile flew 1,500 kilometers. The Dolphin submarines use several key systems to operate. The main control system is the ISIS-91 from ST and Atlas Electronic, which handles weapons, sensors, navigation, and operations. For detecting threats, it has a Timnex radar warning system that can spot radar signals between 5 and 20 GH and can figure out where radar is coming from within 5 to 10 degrees. It also has an ELTA radar for scanning the ocean surface. To detect things underwater, it uses an Atlas Electronic CSU-90 sonar system that can both actively search for objects and passively listen. Another interesting feature of the submarine is its design, which helps it stay hidden in two ways. It has a special prismatic hull shape and smooth connections to its sail, making it harder to detect. It's built with non-magnetic materials, so it won't trigger magnetic mines or be spotted by magnetic sensors. It has 2 Kollmorgen periscopes to see above water and can attach a special compartment behind its sail for carrying special forces teams. The submarines have 3 diesel engines made by MTU Friedrichshafen. These power 3 electrical generators and 1 main motor that turns the propeller. Together, this system gives the submarine enough power for all its operations. The submarine moves faster underwater at 20 knots than when it's near the surface using its snorkel at 11 knots. In June 2009, a submarine went to the Red Sea for training and stopped at Israel's Eilat naval base. Eilat is a small piece of coast between Egypt and Jordan. Israeli media saw this as sending a message to Iran. However, a newspaper wrongly quoted the defense official, saying Eilat isn't a good place for these submarines. The problem is its location. The entrance through the Straits of Tiran is narrow and surrounded by potential enemies, with Saudi Arabia on one side and Egypt's Sinai region on the other. From Israel's main navy base in Haifa, submarines have 2 choices to reach the Persian Gulf. Use the Suez Canal or go the long way around Africa. The Suez Canal option is faster, but means traveling on the surface where everyone can see them. An old treaty from 1888 says Egypt has to let all ships use the canal, no matter which country they're from or whether there's a war on. Egypt blocked Israeli ships from using both the Suez Canal and the Straits of Tiran in 1956 and 1967. Israel responded both times by taking over the Sinai region to break these blockades. Later, the peace treaty between Egypt and Israel fixed this problem. It said Israeli ships could freely use the Suez Canal and that everyone could use the Strait of Tiran and Gulf of Aqaba. Israel may have used submarines to support alleged airstrikes in Sudan, even without access to nearby bases. While the Sudanese government denies any attacks occurred, a couple of Sudanese news outlets reported that Israeli submarines were active off Sudan's coast around the time. The specific timing is unclear, with the media accounts placing the incidents in either November or December 2011. If true, Israel likely relied on submarine tenders, special ships that can resupply and service submarines while at sea, to enable secret underwater operations so far from Israeli ports. This approach of using support vessels is how other militaries have employed submarines when friendly bases were not available in the area. Israel used a submarine to attack Syria's Latakia port in 2013, specifically a Dolphin-class sub-launched long-range missiles at some fancy new Russian anti-ship weapons that Syria had just gotten. The reports say Israel coordinated the strike with the United States and was targeting Yakhant missiles and radars that had recently been unloaded at the port. So in simple terms, it looks like Israel may have teamed up with the United States to take out some serious Russian weapons before Syria could put them to use, and did it by launching missiles from a submarine. On December 2020, Israel sent one of its submarines through the Suez Canal and into the Red Sea. The sub was headed for the Persian Gulf. Why? Israel was worried Iran might try to retaliate for the killing of one of its top nuclear scientists, Mohsen Fakhrizadeh. He was assassinated in November. So Israel wanted to have a submarine ready in the Persian Gulf, just in case Iran decided to strike back. The sub was essentially a warning to Iran and a way for Israel to launch a counterattack quickly if needed. The whole thing shows how tensions are always high between Israel and Iran, and how Israel is ready to use its military might if it feels threatened by sending a submarine to Iran's backyard, which sends a pretty clear message. Now, there is a new Israeli submarine called the Drakon that's being built by a German company. Israel and Germany aren't saying much about it officially, but there's talk that it'll be bigger and have some new tricks up its sleeve. The shipbuilder released some pictures that show the Draken has a new shape and a larger tower-like thing called a sail sticking out of the top. People think that could mean it has room inside to launch missiles straight up, like a vertical launch system. Basically, Israel might be getting a fancy new submarine with more firepower and capabilities than the ones it has now. But until it's finished and in action, a lot is still under wraps. The German company building Israel's new submarine says the Dakar is going to be a totally new design. They're making it specifically to meet what the Israeli Navy needs. No hand-me-down subs here. This one will be custom-made from scratch to get the job done right for Israel. So the mystery is starting to clear up, but there is still a lot we don't know for sure about what this new sub can do. One thing is for certain, though. It's not just another run-of-the-mill submarine. This thing is built specially for Israel, and it's got some unique features to match. An expert named Matus Smutny took a close look at the sub's sail and came up with some interesting ideas about what else it could be used for, besides just missile launchers. He thinks the sail might have a special compartment for releasing underwater drones or even aerial drones. Basically, little robots that can go off and do their own thing. The sail could also be used for special ops missions or to gather intel. Another guess is that the funky new sail design could be a way to test out the technology that will go into Israel's next generation of subs, called the Dakar class. Now, let us move to the United States Virginia-class submarines. Here is a breakdown of what you need to know about the Navy's Virginia-class submarines. 1, they are the newest nuclear-powered fast attack subs in the fleet. The Navy uses them for all sorts of missions in the open ocean and near coastlines. They are especially good at hunting other subs and gathering intelligence. The Virginia class is set to take over from the old Los Angeles class subs, although a bunch of those have already been retired. Reports have it that the Navy plans to keep building Virginia class subs until 2043. They are expected to stay in service for a long time, at least until 2060, while some of the newer ones might even still be around in the 2070. So basically, the Virginia class is the future of the United States submarine force. They are versatile, they are advanced, and they will be the backbone of the fleet for decades to come. They are also part of a three-way defense pact with the United States and the United Kingdom called AUKUS. On March 2023, AUKUS announced that Australia was going to buy 3 Virginia-class subs from the United States, which is a band-aid solution for Australia. They have got these old diesel-powered subs called the Collins class that are on their way out. Eventually, they want to get some new tech subs that the 3 AUKUS countries are going to design together, called the SSN AUKUS class. But here's the thing, if the SSN AUKUS subs get delayed, Australia might be left high and dry without any subs at all. So buying the Virginia-class subs from the United States buys them some time. Just in case, Australia also has the option to buy 2 more Virginia-class subs if they need to. So it's kind of like a submarine safety net for them. These subs have a pretty sweet sonar setup that can be upgraded easily. The sonar arrays use something called an open system architecture. That basically means they can pop in new hardware and software as soon as it's available. The subs get hardware upgrades every 4 years or so. This is called technology insertions, and every 2 years, they get software updates known as advanced processor builds. So what kind of sonar arrays are we talking about? Well, there's a bunch. The first one is a big spherical sonar array on the bow that can send out and listen for sound waves. Some newer subs have an even bigger one called a large aperture bow array. On each side of the hull, there are 3 flat panels, which are part of a lightweight sonar array that uses fiber optics. There are 2 high-frequency sonars, one on the chin, which is located directly under the bow, and one on the sail, which is the tower-looking part. These help the sub operate better close to shore, under ice, and when fighting other subs. Finally, there is something called a low-cost conformal array. It is another high-frequency sonar that's mounted on both sides of the sail. It lets the sub see above and behind it. So in a nutshell, these subs are loaded with all kinds of fancy sonar tech to help them navigate and fight, and it can all be upgraded pretty easily to keep up with the latest and greatest. But wait, there's more. The Virginia-class subs also drag a couple of other sonar arrays behind them. There is the Fat Line Tactical Towed Array, which is either a TB-16 or TB-34, depending on which sub we're talking about. Then there's the Thin Line Long Range Search Array, which could be a TB-29 or TB-33. So between the sonar on the sub itself and these towed arrays, the Virginia-class has a pretty comprehensive way of hearing what's going on under the water, near and far, which makes it a submarine with surround sound. The Fighting Falcon just reached a whole new level. This iconic multi-role fighter, trusted by over 25 countries for its exceptional maneuverability, long combat range, and all-weather targeting, now boasts a cutting-edge engine upgrade. With increased thrust and efficiency, this powerful addition promises to enhance its speed, agility, and operational reach. How will this advancement redefine air combat capabilities? What tactical advantages will it bring to the battlefield? Join us as we unveil the capabilities of the powerful F-110 engine that just transformed the already formidable F-16 into a global threat. The F-16 has always been a force to be reckoned with. Created to dominate the skies during the day, this aircraft was later improved to handle many different missions in all kinds of weather. Since its first production in 1976, more than 4,600 of these versatile planes have been made, showing their continued success and importance in modern air combat. Its ability to adapt to changing needs has made it a reliable choice for various roles, from air defense to ground attacks, solidifying its place as one of the most widely used aircraft in the world. The F-16 may be smaller and lighter than earlier fighter jets, but it is packed with advanced technology that makes it incredibly agile and powerful. One of its most impressive features is its use of advanced aerodynamics and avionics, including a unique flight control system called Relaxed Static Stability / Fly-by-Wire, which improves its maneuverability. The F-16 was the first fighter designed to handle extreme 9G maneuvers, and it can reach speeds faster than Mach 2. This jet is full of innovations designed to improve the pilot's experience and performance. The frameless bubble canopy offers better visibility, while the side-mounted control stick makes it easier to handle. The pilot seat is also reclined, reducing the effects of G-forces during sharp turns. For weaponry, the F-16 has an internal 20mm M61 Vulcan cannon and can carry a range of missiles, bombs, and pods. With a thrust-to-weight ratio greater than 1, it has the power to climb rapidly and accelerate vertically. Designed to be more cost-effective and easier to maintain than older jets, the F-16's airframe is made from 80% aviation-grade aluminum alloys, 8% steel, 3% composites, and 1.5% titanium. The design includes advanced features like bonded aluminum honeycomb structures and graphite epoxy coatings for the flaps and fins. The aircraft has fewer lubrication points and fuel line connections, which makes maintenance quicker and simpler. Around 80% of the access panels can be reached without the need for special stands. The air intake is positioned to reduce drag and ensure the jet performs efficiently. Initially, the F-16 was designed for a 4,000 flight-hour lifespan, with the ability to handle 7.33 G maneuvers. However, engineers went above and beyond, designing the airframe to last for 8,000 hours and handle 9G maneuvers with full fuel. This extra durability proved beneficial as the F-16's role expanded from air-to-air combat to a versatile multi-role aircraft. As the mission requirements evolved, the F-16 gained additional systems, which added weight, prompting several strengthening programs to ensure it could handle the extra load. If this aircraft was initially termed formidable, its new engine, the F-110, has transformed it from a respected aircraft to a global threat. How exactly did this engine transform this respected United States multi-role fighter? Let's check out what exactly makes this engine revolutionary. The General Electric 110 is a powerful jet engine designed to boost fighter aircraft performance. It was built by GE Aerospace, uses an afterburning turbofan system, and was created as an alternative to the Pratt & Whitney F-100. The F-110 was originally developed from the F-101 engine and first used in the F-16C Fighting Falcon and F-14A+ and B Tomcat. Over time, it was also chosen to power newer versions of the F-15 Eagle. This engine is manufactured not only in the United States, but also internationally through licensing agreements. IHI Corporation in Japan, TUSA's Engine Industries in Turkey, and Samsung Techwin in South Korea all produced the F-110. During the 1970s, General Electric aimed to re-enter the U.S. fighter engine market while the Air Force searched for solutions to the reliability and maintenance problems of its Pratt & Whitney F-100 engines used in F-15s and F-16s. GE began developing the F-101X, an improved version of the F-101 engine, originally designed for the B-1 bomber. This new design featured a smaller fan borrowed from the F-404 engine, making it more suitable for fighter jets. The Iris nozzle, also from the F-404, was adapted for this engine. When the Carter administration canceled as the B-1A bomber, GE shifted its focus, hoping to offer the F-101X to the fighter market. The Air Force showed interest and started funding the project, renaming it the F-101 Derivative Fighter Engine. This competition was part of a broader effort to push Pratt & Whitney to improve the F-100. In 1980, the F-101 DFE completed ground tests and was fitted on an F-16 for flight testing, demonstrating significant performance gains. By 1982, the Air Force committed to full-scale development, eventually naming it the F-110 GE-100. This sparked the so-called Great Engine War in 1983, a fierce competition between the F-100 and F-110 engines. Contracts were awarded annually based on performance and cost, resulting in both engines being used by the Air Force until the competition ended in 1992. The F-101 DFE also showed its potential on the Navy's F-14B prototype in 1981, outperforming the TF-30 engine. While initial testing was paused, the Navy later adopted the engine, designating it as the F-110 GE-400 for future F-14s. GE's persistence and innovation allowed the F-110 to become a key player in military aviation. In the mid-1980s, the U.S. Air Force wanted more powerful engines for its tactical fighters, leading to the Improved Performance Engine program. This resulted in the F-110 GE-129, which increased thrust to 29,900 pounds in the afterburner. It introduced new technologies like a digital engine control system, allowing higher thrust in more conditions. It debuted in 1992 with the F-16C and D Block 50, and later upgraded F-15E variants, starting with the F-15K in South Korea. The F-16 Fighting Falcon originally entered service with the Pratt & Whitney F-100 afterburning turbofan engine. However, to reduce costs and improve efficiency, the United States Air Force launched the Alternate Fighter Engine program in 1984. This initiative allowed engine manufacturers to compete for contracts, leading to the adoption of the General Electric F-110 engine. By June 2005, an impressive 86% of the USAF's F-16 CD fleet was powered by F-110 engines. The F-110 GE-100 offered about 4,000 pounds more thrust than the F-100 PW-200, but it required additional airflow to perform at its peak. The standard inlet design, known as the normal shock inlet, restricted the F-110 thrust to 25,000 pounds. To solve this, engineers introduced a larger inlet design called the Modular Common Inlet Duct, also nicknamed Big Mouth. The F-16C and D Block 30 and Block 32 were the first variants to feature a common engine bay, allowing them to accommodate both the F-100 and F-110 engines. The Block 30 models were equipped with the larger MCID inlet for the F-110, while Block 32 retained the standard NSI inlet for the F-100. The F-16C and D Block 30 and 40 aircraft used the F-110 GE-100 engine, producing 28,000 pounds of thrust. Later, the Block 50 variant introduced the F-110 GE-120-9 improved performance engine, boosting thrust to 29,500 pounds. For the advanced F-16E and F Block 60 used by the United Arab Emirates, the F-110 GE-132 was developed, delivering an even more impressive 32,500 pounds of thrust. This engine was also proposed for the Lockheed Martin Tata F-21, a Block 60-based model aimed at the Indian Air Force's Marca competition. The latest production model, the F-16C Block 70, features the F-110-129D engine, which is designed for greater durability and a longer lifespan. Two F-16 derivatives, the Mitsubishi F-2 and the General Dynamics F-16XL, also use the F-110-129 IPE engine. For the F-2, the engines were built under license by Japan's IHI Corporation, where they were designated as the F-110 IHI-129. However, in 2024, IHI Corporation faced scrutiny after a whistleblower revealed that its subsidiary, IHI Power Systems Company, had been falsifying engine data since 2003. This scandal affected over 4,000 engines worldwide. Japan's Ministry of Land, Infrastructure, Transport, and Tourism launched an investigation into the matter in April 2024, casting a shadow on IHI's reputation. Despite this, the F-110 remains a cornerstone of the F-16 program, showcasing its adaptability and performance in various configurations across decades. Now, as the iconic F-16 Fighting Falcon celebrates 50 years of service, it's a perfect time to look ahead and explore how this legendary fighter will continue to meet modern and future challenges. While the U.S. Air Force is gradually retiring older F-16 models, the newer Block 40 and Block 50 variants are set to remain in action well into the 2040s. To stay relevant, these aircraft will undergo significant upgrades to enhance their performance and combat capabilities, even more upgrades than equipping it with a fearsome engine. To this effect, a total of 608 Block 40 and Block 50 F-16s, often referred to as post-block aircraft, will receive these critical upgrades as part of the Post-Block Integration Team initiative. This ambitious program, led by the Air Force Lifecycle Management Center's Fighters and Advanced Aircraft Directorate, involves up to 22 advanced modifications designed to boost the F-16's lethality and adaptability. These upgrades aim to ensure the fourth-generation fighter stays effective against evolving threats in a rapidly changing battlefield. From modernizing avionics and radar systems to enhancing weapon capabilities and survivability, the POBIT project reflects the Air Force's commitment to keeping the F-16 relevant and combat-ready for decades to come. This effort ensures that the F-16's remarkable legacy will continue to soar, even in the face of future challenges. Former Air Force Chief of Staff General C.Q. Brown, Jr. expressed optimism about the ongoing upgrades to the F-16. He highlighted that these improvements would enhance the aircraft's combat effectiveness and adaptability in an ever-evolving electronic warfare environment. Brown emphasized the importance of modernizing the F-16 to maintain air superiority in the future. The Post-Block Integration Team Upgrade Program, which was launched in 2022, is being implemented alongside the Service Life Extension Program, or SLEP. The SLEP focuses on extending the aircraft's operational life from 8,000 to 12,000 flight hours. This involves extensive structural modifications, including replacing bulkheads and longerons, strengthening wing assemblies, adding new brackets and beams, and reskinning the upper fuselage. Each aircraft undergoes a detailed 9-month refurbishment process at multiple locations across the United States and Europe. A major component of the POBIT upgrades is the integration of advanced technology. The APG-83 Scalable Agile Beam Radar, equipped with active electronically scanned array, is a key feature of the program. Alongside the center display unit, the new radar system provides pilots with enhanced situational awareness. It allows for synthetic aperture radar mapping, enabling the detection and engagement of both air-to-air and air-to-ground threats at significantly longer ranges. These upgrades are expected to transform the F-16 into a more capable and resilient aircraft. By combining structural improvements with cutting-edge technology, the program aims to ensure that the F-16 remains an essential asset for modern combat operations well into the future. The F-16 is also getting new improvements like the Link 16 for better data sharing, updating the cockpit and mission computer, and switching to a high-speed data network. The upgrades also bring next-generation electronic warfare systems, a communication suite upgrade, and a programmable data generator, along with several other advanced hardware changes. These updates are being introduced in phases to keep the F-16s operational while modernizing the fleet. The oldest F-16s in the post-block fleet are the Block 40 and 42 models, which started production in late 1988. The newest is a Block 50, delivered in March 2005. Before the POBIT program, the biggest upgrade was the Common Configuration Implementation Program, which ran from 2000 to 2010. This effort brought 651 Block 40, 42, 50 and 52 variants to a common standard with major improvements, such as new mission computers, updated cockpit displays, and improved data links. Later, the focus shifted to adding an advanced AESA radar, which had been long overdue. Early attempts didn't succeed, but a new opportunity came when the U.S. Northern Command identified an urgent need for a radar upgrade for pre-block F-16s used by the Air National Guard for Homeland Defense. The Air Force chose the Northrop Grumman AN/APG-83 S-Sabre radar for this mission. After its success with the Air National Guard, the same radar was selected for active-duty F-16s, ensuring that all operational F-16s benefit from this powerful technology. The F-16 is also receiving a variety of advanced upgrades to enhance its combat capabilities, starting with the powerful new radar system from Northrop Grumman. This radar is designed to fit the F-16 without needing any structural changes, power adjustments, or cooling upgrades. It enables the F-16 to detect, track, and identify more than 20 targets at once, faster and at greater distances. Additionally, the radar includes synthetic aperture radar mapping, which provides high-resolution images in all weather conditions. The system also has strong electronic protection, allowing it to operate effectively in challenging electronic warfare environments. Another key upgrade is the addition of the center display unit, first installed in Air National Guard jets in 2010. The CDU replaces the old instruments on the center pedestal with a high-resolution, multi-function color display. This upgrade helps pilots take full advantage of the new radar and improve targeting pods, while also reducing their workload and enhancing safety and efficiency during missions. As part of the Post-Block Integration Team program, the F-16 is also receiving the Northrop Grumman N/ALQ-257 Integrated Viper Electronic Warfare Suite. This next-generation system replaces older electronic warfare equipment and is fully integrated with the new APG-83 radar. The IVUS is designed to meet the requirements of open mission systems and offers long-term growth potential to accommodate future upgrades, such as the fiber optic tow decoy and adaptive processing. The suite also includes a radar warning receiver, though some details are still unclear due to an ongoing contract with Raytheon for additional radar warning receivers. One major benefit of the IVEWs is that it is completely internal to the aircraft, removing the need for external electronic countermeasure pods like the ALQ-131 and ALQ-184. This allows the F-16 to use the centerline station for external fuel tanks or other payloads, maximizing its versatility. The IVWs can also jam current and future threats, greatly enhancing the aircraft's ability to defend itself in hostile environments. Alongside these upgrades, the F-16 is receiving improvements in countermeasures as well. The weapon pylons on stations 3 and 7 have been equipped with Terma's Pylon Integrated Dispenser System, which improves the capacity for chaff and flare countermeasures. Additionally, a contract signed in 2020 will deliver the new Pylon Integrated Dispensing System Universal, featuring 3 chaff flare dispenser magazines and provisions for future missile warning systems. The Air National Guard is also introducing new systems, such as the ASQ-236 Dragon's Eye AESA radar pod, which offers detailed surveillance maps and coordinates for bomb impact assessments. This system complements the APG-83 radar, making the F-16 even more capable in combat. Another exciting development is the fielding recommendation for Leonardo's Bright Cloud 218 expendable active decoy. The Bright Cloud is a self-contained, battery-powered decoy that can be dropped from the aircraft to confuse incoming missiles. It creates a significant distance between the aircraft and the decoy, allowing the missile to miss the aircraft entirely. These upgrades are just part of the many improvements the F-16 is receiving, with more developments expected as technology continues to evolve. The F-16's enhancements ensure that it remains a formidable force in modern air combat, adapting to new challenges and maintaining its effectiveness for years to come. To keep the aircraft in peak condition, every time an F-16 reaches 400 flight hours, it undergoes a major inspection in the phase dock. During this process, 136 panels are removed to thoroughly check the areas beneath them. Along with the 400-hour inspection, Other checks are conducted to ensure the aircraft is fully operational. The inspection process is a team effort, involving F-16 crew chiefs and specialists from various fields like weapons, avionics, and fuel shops. Through careful coordination, the aircraft is made ready to return to service, fit to fly and perform its mission effectively. The goal of this phase is to ensure that the pilots get 400 more safe flight hours before the aircraft comes back for another inspection. Just like any vehicle, the F-16 Fighting Falcon needs regular maintenance and repairs. Most of the maintenance can be done with the engine still in the jet, but for some major fixes, the entire engine has to be removed. For instance, when we discover a damaged hydraulic line, it is not possible to repair it with the engine in place, so it's necessary to remove the engine to replace the line. Before the engine can be removed, the jet must be disarmed, and the weapons must be carefully taken off the F-16 wings to ensure safety. Once the weapons are removed, the process of detaching the engine from the airframe can begin. It takes over an hour to separate the engine and then carefully pull it out of the aircraft. The engine is heavy, and as it comes out, it can cause the aircraft to shift. The crew have to be careful and make sure the aircraft stays level as the engine is pulled out, so it doesn't put extra strain on the airframe. With the engine safely removed, the hydraulic line is replaced, and then the maintenance team continues with repairs on the rest of the F-16s. Each task is important, and working as a team ensures that the jets are always ready to return to action. For decades, tension between North Korea and the United States has festered. While these tensions rarely lead to direct conflict, there are moments when they heat up, forcing both nations to show their strength. These clashes often reveal advanced military technology and weapons. But what could push these tensions into open conflict? And what kinds of advanced armaments might we see in action? Join us as we delve into how North Korea battles U.S. carrier aircraft made with alien technology. The long-standing tensions between North Korea and the United States have been steadily escalating, and it appears they have now reached a critical juncture, with both nations showing signs of abandoning restraint. In October 2024, North Korea confirmed that it launched a new intercontinental ballistic missile, ICBM, towards waters off its eastern coast in what was the longest flight time yet for a North Korean missile. This raised fears of advanced weapons development by Pyongyang. The official Korean Central News Agency, KCNA, said its leader, Kim Jong-un, was present at the missile test launch and issued a warning to his enemies. According to him, the test fire is an appropriate military action that fully meets the purpose of informing the rivals, who have intentionally escalated the regional situation and recently threatened the security of the Republic, of their counteraction will. The missile flew for 86 minutes and approximately 1,000 kilometers at a maximum altitude of 7,000 kilometers before it splashed down off the coast of Hokkaido, outside Japan's exclusive economic zone, according to Japan's defense agency. North Korean state media confirmed that an ICBM was launched to inform rivals of the country's powerful capabilities. Test launching long-range missiles plays a vital role in North Korea's military development process, as leader Kim Jong-un wants to acquire a vast arsenal of missiles and nuclear weapons that analysts say are capable of one day reaching targets as far as Japan and the US. Test-firing ICBMs helps the North refine its weapon systems. It is also the way North Korea grabs the world's attention during key events. Shin Seong-ki, head of research on North Korea's military at the state-run Korea Institute for Defense Analyses in Seoul, told the Reuters news agency, the ICBM test launch was intended to show that North Korea will not bow to pressure, as Pyongyang has recently come under pressure over the reported deployment of an estimated 10,000 North Korean soldiers to assist Russia in Ukraine. The test sends a message that North Korea will respond to strength with strength. However, this is not the first time North Korea has sent a warning to the world through its missile testing. In December 2023, North Korea set the world on edge when it tested some of its newest weaponry. Pyongyang last test-fired an ICBM in December 2023 with the launch of its powerful Hwasong-18 missile, marking the third time North Korea tested the weapon. According to 38 North, a program at the Stimson Center think tank in Washington, D.C., that monitors North Korea, the Hwasong-18 flew a reported 1,000 kilometers for about 73 minutes at an altitude of more than 6,000 kilometers. ICBMs are designed to fly long distances and carry weapons such as nuclear warheads. The December missile was launched at a lofted trajectory, the same as the one launched almost a year later. Although impressive, the Hwasong-18 is not quite as impressive as the ICBM test launch this year. Lofted trajectory simply means firing a missile almost vertically. This allows the missile to travel to a very high altitude, but then land a short horizontal distance from the launch site. Lofted launches are said to enable Pyongyang to gather data sent back from test missiles to understand better the challenges faced when a long-range warhead re-enters the Earth's atmosphere at extremely high speed and generates tremendous amounts of heat. Analysts say the Hwasong-18 could fly as far as 15,000 kilometers when fired in a non-lofted trajectory. The Hwasong-18 also marked a departure from past ICBM models, such as the Hwasong-17, because it was a solid-state fuel missile, which is safer and easier to maneuver than liquid-propelled missiles. It is a three-stage solid-fueled intercontinental ballistic missile, ICBM. Solid-fueled missiles use a solid propellant composed of fuel and oxidizer that is tightly packed into the rocket's motor. This mixture is stable and can be stored for long periods without significant degradation. Solid-fueled ICBMs have shorter launch preparation times because the propellant is already inside the missile, making them more responsive to sudden launch orders. Solid-fueled ICBMs are typically more mobile, as they can be easily transported on vehicles without the need for additional fueling equipment. A three-stage ICBM is a type of ICBM with three stages, or sections, that propel the missile to its target. The first stage is the boost stage, which is responsible for lifting the missile off the ground and accelerating it to a high velocity. The boost stage typically uses a liquid-fueled rocket engine, which provides a high amount of thrust for a short period. Once the missile has reached a certain altitude and speed, the first stage falls away, and the mid-course stage takes over. The mid-course stage guides the missile toward its target using a combination of internal guidance systems and external tracking systems. The final stage of the missile's flight is the terminal stage, which is responsible for ensuring that the missile reaches its target with precision. The terminal stage typically uses a small rocket engine, which can make fine adjustments to the missile's trajectory to ensure that it hits its target. However, due to the secretive nature of North Korea's missile program, it is difficult to ascertain the exact details of the guidance system employed. The United States did notice North Korea's activities, much to the displeasure of North Korea, which is allies to North Korea's rivals, namely South Korea and Japan. North Korean leader Kim Jong-un did not waste time in renewing his call for a limitless expansion of his military nuclear program to counter the United States-led threats in comments reported that were his first direct criticism toward Washington since Donald Trump's win in the United States presidential election. At a conference with Army officials, Kim condemned the United States for updating its nuclear deterrence strategies with South Korea and solidifying three-way military cooperation involving Japan, which he portrayed as an Asian NATO that was escalating tensions and instability in the region. One of the reasons for the escalating tensions between North Korea and the United States is the war between Russia and Ukraine. Kim criticized the United States over its support of Ukraine against a prolonged Russian invasion. He insisted that Washington and its Western allies were using Ukraine as their shock troops to wage a war against Moscow and expand the scope of United States military influence, the North's official Korean Central News Agency said. In recent months, Kim has prioritized his country's ties to Russia, embracing the idea of a new Cold War and displaying a united front in Russian President Vladimir Putin's broader conflicts with the West. He has yet to directly acknowledge that he has been providing military equipment and troops to Russia to support its war against Ukraine, and the KCNA's report didn't mention whether Kim made any comments toward Trump, whose election win has yet to be reported in the North state media. North Korean leader Kim Jong-un vowed his country would invariably support Russia's war in Ukraine as he met Russia's defense chief. A Russian military delegation led by Defense Minister Andrei Belousov arrived in North Korea amid growing international concern about the two countries' expanding cooperation after North Korea sent thousands of troops to Russia last month. The official Korean Central News Agency said that Kim and Belousov reached a satisfactory consensus on boosting strategic partnership and defending each country's sovereignty, security interests, and international justice in the face of the rapidly changing global security environments in a meeting. He said that North Korea will invariably support the policy of the Russian Federation to defend its sovereignty and territorial integrity from the imperialist moves for hegemony. North Korea has supported Russia's invasion of Ukraine, calling it a defensive response to what both Moscow and Pyongyang call NATO's reckless eastward advance and United States-led moves to stamp out Russia's position as a powerful state. He criticized a United States decision earlier in November to let Ukraine strike targets inside Russia with the United States-supplied longer-range missiles as a direct intervention in the conflict. He called recent Russian strikes on Ukraine a timely and effective measure to demonstrate Russia's resolve. According to United States, Ukrainian, and South Korean assessments, North Korea has sent more than 10,000 troops to Russia, and some of them have already begun engaging in combat on the front lines. The United States, South Korea, and others say North Korea has also shipped artillery systems, missiles, and other conventional weapons to replenish Russia's exhausted weapons inventory. Both North Korea and Russia haven't formally confirmed the North Korean troops' movements and have steadfastly denied reports of weapons shipments. The United States, not one to just sit back and watch a display of power, decided to respond in a show of force of its own. This nation flew a long-range bomber in a trilateral drill with South Korea and Japan in response to North Korea's test firing of a new intercontinental ballistic missile designed to strike the United States mainland. North Korea on Thursday tested the newly developed Hwasong-19 ICBM, which flew higher and stayed in the air longer than any other missile it has fired. North Korean leader Kim Jong-un called it an appropriate military action to cope with external security threats posed by its rivals. The United States flew the B-1B bomber to train with South Korean and Japanese fighter jets near the Korean Peninsula, demonstrating the three countries' firm resolve and readiness to respond to North Korea's advancing nuclear and missile programs. South Korea's Joint Chiefs of Staff said in a statement, "The B-1B carries the largest conventional payload of both guided and unguided weapons in the Air Force inventory. The multi-mission B-1 is the backbone of America's long-range bomber force. It can rapidly deliver massive quantities of precision and non-precision weapons against any adversary, anywhere in the world, at any time. The B-1B's blended wing and body configuration, variable geometry wings, and turbofan afterburning engines combine to provide long-range maneuverability and high speed while enhancing survivability. Forward wing settings are used for takeoff, landings, air refueling, and in some high-altitude weapons employment scenarios. Aft wing sweep settings, the main combat configuration, are typically used during high subsonic and supersonic flight, enhancing the B-1B's maneuverability in the low and high-altitude regimes. Its speed and superior handling characteristics allow it to integrate seamlessly into mixed force packages. These capabilities, when combined with its substantial payload, excellent radar targeting system, long loiter time, and survivability, make the B-1B a key element of any joint and composite strike force. It is a highly versatile multi-mission weapon system. Its synthetic aperture radar is capable of tracking, targeting, and engaging moving vehicles, as well as self-targeting and terrain-following modes. In addition, an extremely accurate global positioning system-aided inertial navigation system enables aircrews to navigate without the aid of ground-based navigation aids and engage targets with a high level of precision. The addition of a fully integrated data link, FIDL, with Link 16 capability provides improved battlefield situation awareness and secure beyond line-of-sight reachback connectivity. In a time-sensitive targeting environment, the aircrew can use targeting data received from the Combined Air Operations Center or other command and control assets to strike emerging targets rapidly and efficiently. The B-1B's onboard self-protection electronic jamming equipment, radar warning receiver, ALQ-161, expendable countermeasures, chaff and flare system, and tow decoy system, AL-50, complement its low radar cross-section to form an integrated, robust defense system that supports penetration of hostile airspace. The ALQ-161 electronic countermeasure system detects and identifies the full spectrum of adversary threat emitters and then applies the appropriate jamming technique either automatically or through operator inputs. Current modifications build on this foundation. Radar sustainability and capability upgrades will provide a more reliable system and may be upgraded in the future to include an ultra-high-resolution capability and automatic target recognition. The addition of Link 16 and FIDEL, combined with associated cockpit upgrades, will provide the crew with a much more flexible, integrated cockpit and allow the B-1 to operate in the fast-paced integrated battlefield of the future. Several obsolete and hard-to-maintain electronic systems are also being replaced to improve aircraft reliability. The B-1A was initially developed in the 1970s as a replacement for the B-52. 4 prototypes of this long-range, high-speed Mach 2.2 strategic bombers were developed and tested in the mid-1970s. Still, the program was canceled in 1977 before going into production. Flight testing continued through 1981. The B-1B is an improved variant initiated by the Reagan administration in 1981. Significant changes included an additional structure to increase payload by 74,000 pounds, an improved radar, and a reduction of the radar cross-section by an order of magnitude. The inlet was extensively modified as part of this RCS reduction, necessitating a reduction in maximum speed to Mach 1.2. The first production B-1 flew in October 1984, and the first B-1B was delivered to Dyess Air Force Base, Texas, in June 1985. Initial operational capability was achieved on October 1, 1986. The final B-1B was delivered May 2, 1988. The United States eliminated the nuclear mission for the B-1 in 1994. Even though the Air Force expended no further funding to maintain nuclear capabilities, the B-1 was still considered a heavy bomber equipped for nuclear armament until 2007. The conversion to conventional only began in November 2007 under the original START Treaty and was completed in March 2011 under the New START Treaty. To make that conversion possible, 2 steps were taken. During the first step, a metal cylindrical sleeve was welded into the aft attachment point of each set of B-1 pylon attachments. This prevented installing B-1 air-launched cruise missile pylons. During the second step, 2 nuclear armament unique cable connectors in each of the B-1 weapons bays were removed. This prevented the pre-arm signal from reaching the weapons. The B-1B holds almost 50 world records for speed, payload, range, and time of climb in its class. The National Aeronautic Association recognized the B-1B for completing one of the 10 most memorable record flights for 1994. The most recent records were made official in 2004. The B-1B was first used in combat in support of operations against Iraq during Operation Desert Fox in December 1998. In 1999, 6 B-1s were used in Operation Allied Force, delivering more than 20% of the total ordnance while flying less than 2% of the combat sorties. During the first 6 months of Operation Enduring Freedom, 8 B-1s dropped nearly 40% of the total tonnage delivered by coalition air forces. This included almost 3,900 JDAMs, or 67% of the total. In Operation Iraqi Freedom, the aircraft flew less than 1% of the combat missions while delivering 43% of the JDAMs used. The B-1 continues to be deployed today, flying missions daily in support of continuing operations. The trilateral aerial training was the second by South Korea, the United States, and Japan in 2024, the statement read. The United States often responds to major North Korean missile tests with temporary deployments of some of its powerful military assets, such as long-range bombers, aircraft carriers, and nuclear-powered submarines to and near the Korean Peninsula. North Korea typically responds angrily to such United States actions, calling them part of a United States-led plot to invade the North and perform additional weapons tests. Although the United States engaged in trilateral aerial training with South Korea and Japan, it is more than capable of defending itself on its own and maintaining its status as the world's leading military country. In terms of intercontinental ballistic missiles, the United States has some of the world's most cutting-edge technologies. The United States launched Minuteman III in an essential test of the weapon's ability to strike its targets with multiple warheads. The Minuteman III missiles that form a critical leg of the United States nuclear triad each carry 1 nuclear-armed re-entry vehicle. But the missile that was tested carried 3 test warheads. After a United States Navy E-6B Mercury transmitted the launch command, the Minuteman III blasted out of a silo at the launch facility on the north side of this base on the California coast. Airmen from the 625th Strategic Operations Squadron of Offutt Air Force Base were aboard the E-6 along with Navy aircrew. The three test re-entry vehicles, one high-fidelity joint test assembly, which carries non-nuclear explosives, and two telemetry joint test assembly objects, struck the Reagan test site near the Kwajalein Atoll in the Marshall Islands roughly 30 minutes later after launch, a flight of about 4,200 miles. Colonel Dustin Harmon, the commander of the 377th Test and Evaluation Group, the nation's operational ICBM test unit, said in an interview with Air and Space Forces magazine that they make up essentially a warhead. According to him, there are two different types. One is telemetered, and it has a radio transmitter in it. It has antennas, gyroscopes, accelerometers, and all the things that can sense motion. They fly those, or they can put one in there that's called a high fidelity. War is brewing, and the threat of hypersonic missiles has intensified. As a response to these unsettling tensions, Israel is set to reveal a $1 billion laser weapon that could change everything. This powerful new system is designed to destroy hypersonic missiles, marking a huge leap in defense technology. As rivals like Iran race to build advanced weapons, Israel has made a bold move to protect itself and shift the balance of power. How does this incredible laser weapon work, and what does it mean for future conflicts? Join us as we explore the amazing features of the new 2025 $1 billion laser weapon that can destroy all hypersonic missiles. The Middle East has always been a region of intense geopolitical tensions, and this year is no different. On April 13, 2024, Israel found itself under massive aerial attacks. Iran launched over 300 drones and missiles toward Israeli cities, and a group of militants also attacked with dozens of rockets targeting Israeli Defense Force positions. The Golan lit up with explosions as Israel's multi-layered defense system quickly kicked into action. From the Iron Dome to David's Sling, Israel's defenses were overwhelmed but not broken. However, several Iranian missiles managed to slip through and hit many military installations. It became clear that even though Israel's defenses were strong, they weren't completely unbeatable. This attack was a clear warning, and Israel needed something more advanced. That's where the project came in, and now a powerful laser weapon is ready to change the game in missile defense in 2025. The world might have seen many impressive weapons, but the Iron Beam is not an ordinary defense system. It operates with lasers. It was Israel's answer to the growing threat of missile attacks, particularly from countries like Iran, who were deploying more accurate and faster missiles. The Iron Beam, with its nearly infinite capacity to fire, has provided Israel with a solution for their missile problems. The missile defense systems in Israel were found to have weaknesses after the April strike, which caused the defense sector to reconsider how future wars will be handled. The solution is a weapon that could instantly destroy all missiles rather than using traditional missile interceptors. This discovery led to the creation of a $1 billion laser weapon system designed to fight back hypersonic missiles, one of the most terrifying military threats. Hypersonic missiles represent the highest level of military technology. These weapons are quick and flexible, with a maximum speed of 3,800 miles per hour, or more than Mach 5. Traditional missile defense systems, which depend on radar-guided interceptors, are vulnerable to hypersonic missiles. They are the highest level of modern combat, a terrifying combination of agility and accuracy. As countries such as China and Russia developed these advanced technologies, it became clear that the capacity to defend against hypersonic missiles would be at the center of the next important weapons war. The most advanced defense systems were being rendered useless in this war. Israel is taking the whole situation seriously. They had always taken great pride in being the first to use new military technologies, and they were exploring the limits of what was possible in terms of defense with the Iron Beam. As a matter of fact, the Iron Beam is going to act as the foundation for a far bigger project, which is a laser defense system that is anticipated to be available by 2025. And while the Iron Beam is impressive, the next generation of laser technology will be capable of stopping hypersonic missiles. The idea of using light as a weapon is not new, but advancements in laser technology have finally made it possible. This new powerful laser weapon system operates at the speed of light, the fastest known speed in the universe. Traditional missile interceptors are fast, but they cannot keep up with hypersonic missiles. These limitations do not apply to lasers. When a hypersonic missile is detected, the laser locks on, and within a fraction of a second, it begins to destroy the missile. The ability to intercept hypersonic missiles with lasers is an important development in defense technology. But this new weapon's advantages go far beyond its speed. The laser system is also highly cost-effective. Traditional missile defense relies on interceptors, which cost millions of dollars per shot. Each time an Iron Dome missile intercepts a custom rocket, the cost is high, particularly considering that the rockets themselves may only cost a few $100s to produce. In contrast, the cost of firing the laser weapon is around $3 to $5 per shot. This cost-effectiveness addresses sustainability, which is a critical issue in modern warfare. The expense of using interceptor missiles to defend a country might quickly become unmanageable during an extended war. But with a laser weapon, the only requirement is power. As long as the system has a reliable energy source, it can continue firing indefinitely. This makes it a perfect solution for countering mass missile barrages, which are often used to overwhelm traditional defenses. Furthermore, this new laser system is capable of taking on a wide range of threats due to its versatility and effectiveness against hypersonic missiles. This laser weapon can deal with any kind of missile, including conventional missiles and drones. Because of its ability to adapt, it will be an important aspect of defense plans in the future, especially when new technologies change the face of war. Hypersonic missiles, for all their advantages, have one significant weakness, which is that they generate an enormous amount of heat as they travel through the atmosphere. This heat makes them easy targets for lasers. The laser system works by focusing an intense beam of energy onto the missile, rapidly heating its surface until it melts. The missile is destroyed mid-flight, long before it can reach its main target. The accuracy of this laser is unmatched. Traditional interceptors may destroy a missile by crashing into it, but this usually leaves pieces in the air. By guaranteeing that the missile completely breaks down and lowering the possibility of further damage on the ground, the laser weapon eliminates this issue. This is important in highly populated regions where individuals might be seriously harmed by falling missile debris. The importance of this type of defense has been shown by the number of missile assaults that Israel has faced. As seen by the events in April 2024, even the most powerful defense systems are vulnerable to attack. Israel required a defensive system that could keep up with Iran and its allies' ongoing developments in missile technology. This new laser weapon is a game changer not only for Israel, but for any nation facing the threat of hypersonic missiles. The new laser system is a component of a larger plan to include cutting-edge technologies in missile defense. It will completely change the face of warfare. Countries won't need to invest in expensive interceptors to defend themselves from missile assaults. Rather, they will have a defensive system that can stop even the most advanced weapons in use. Even the most powerful defenses were exposed by the missile assault on Israel in April. A small number of projectiles were still able to pass through, even though the Iron Dome, David's Sling, and Arrow missile interceptors had effectively stopped the majority of the incoming threats. After examining the aftermath, Israeli military strategists came to the conclusion that time was running out for their air defense strategy. This was made clearly obvious in October when Iran carried out a second, more complex coordinated attack using drones, ballistic missiles, and cruise missiles. The world witnessed the pressure that Israel's strong missile defense network was starting to show. The sky over Israel suddenly became filled with fire and smoke. As interceptor systems launched their defensive countermeasures, missiles shot into the air at high speed. Traditional defense strategies failed to stop the missiles that managed to evade the interceptors. The iron beams was immediately used, and the outcomes were amazing. This use of laser weapons signified an important change. Although Israel had been working on its iron beam system for a while, the application of laser technology to stop advanced missile threats opened up new possibilities for military defense. The iron beam was capable of accurately eliminating hypersonic and advanced ballistic missiles, in addition to drones and short-range rockets. The iron beam was successful not only because of its speed, but also because it didn't require reloading. No matter how advanced, traditional interceptor missiles have a limited supply. They need time and energy to reload and adjust when they are started, but the iron beam can fire for as long as there is power. This makes it a very useful tool in long battles when waves of missiles might be fired rapidly one after the other. Even though the iron beam is amazing, it is only the start. defense engineers in Israel had already set their minds on something much more cutting edge, and that is a laser weapon capable of stopping hypersonic missiles. Hypersonic missiles, which move at speeds exceeding Mach 5, are the ultimate challenge for any missile defense system. They travel so fast and with such unpredictable flight paths that even the most advanced radar systems can struggle to track them. Once detected, the chance of opportunity to intercept them is quite narrow. Traditional missile defense systems, which rely on physical interceptors, cannot react quickly enough to destroy these hypersonic missiles. The few seconds of delay between detection and interception are all it takes for a hypersonic missile to reach its target. However, the new laser weapon being developed by Israel and its defense partners promises to change the game. Unlike traditional interceptors, the laser weapon operates at a speed of 186,000 miles per second. This means that once a hypersonic missile is detected, the laser can engage it almost instantly, making it the fastest and most reliable defense system against these high-speed threats. Moreover, the laser doesn't just stop at one missile. Its rapid-firing capability allows it to engage multiple targets simultaneously, taking down entire waves of missiles without needing to pause for reloading. It's obvious that Israel's advancements in laser defense technology will have an important impact worldwide as countries observe them. Nations like China, Russia, and the United States are already making significant investments in hypersonic missile technology, starting a new weapon race that will probably influence how conflict is conducted on a worldwide scale in the future. Because of their speed, agility, and capacity to avoid traditional missile defense systems, hypersonic missiles are viewed as a weapon that has the potential to change the game. However, the power balance is starting to change with the introduction of laser weapons. Having a defense system that can destroy any missile, no matter how quick or advanced, is crucial in an area where missile attacks are a constant issue. With this laser technology, Israel is bringing in a new era of defense, one in which the speed of light itself serves as the strongest barrier. The last missile attack on Israel was a reminder of the constant dangers the country faces. Even with its advanced air defense systems, Israel knew it needed something more to stay ahead of its enemies. Alongside this advanced laser system, Israel already has an impressive arsenal of weapons for defending itself. The Iron Dome is one of the most well-known and effective missile defense systems in the world. It is designed to intercept and destroy short-range rockets and artillery shells fired from distances of 4 to 70 kilometers. Since its deployment, the Iron Dome has saved countless lives by stopping rockets aimed at civilian areas. Traditional missile defense systems, like the Iron Dome, need to reload after they fire all their interceptors, but the new laser weapon also reduces the need for reloading and resupplying, which is a huge advantage in the middle of a battle. Another key part of Israel's defense is David's Sling, a medium to long-range missile defense system. It can intercept aircraft, drones, and ballistic missiles. David's Sling complements the Iron Dome by providing an additional layer of protection, targeting missiles that fly at higher altitudes or over longer distances. Then there's the Arrow system, which is specifically designed to intercept long-range ballistic missiles, the kind that can reach speeds of several thousand kilometers per hour and travel across continents. Together, these systems form a multi-layered defense network that has proven to be incredibly effective in keeping Israel safe from missile threats. But as the missile technology of Israel's enemies becomes more advanced, even these impressive systems need help. That's where the laser weapon comes in. By adding laser technology to its defense network, Israel can deal with new threats more advanced than hypersonic missiles that are faster and more unpredictable for traditional missile interceptors to handle. This game-changing technology isn't just limited to defending against missiles either. It can also be used to target drones, which have become an increasingly common threat in modern warfare. In recent years, drones have been used by various groups to carry out surveillance, drop explosives, and even launch attacks on military bases. Israel, like many other countries, has to adapt to the growing use of drones on the battlefield. The laser weapon offers a solution to this problem by being able to track and destroy small, fast-moving drones with ease. Its ability to fire rapidly means that even a swarm of drones can be taken down before they reach their target. The potential for this new technology is big. Not only does it offer a solution to hypersonic missiles and drone swarms, but it could also eventually be used in space-based defense systems, targeting threats before they even enter Earth's atmosphere. The development of this advanced laser weapon marks a turning point in defense technology, as it provides a way to protect against threats that were previously considered unstoppable. Looking ahead, this laser technology will become a critical part of how nations defend themselves against the growing dangers of hypersonic missiles, drones, and other advanced weapons. Israel's investment in this technology shows that they are not just preparing for the threats of today, but also for the challenges of tomorrow. As impressive as the Iron Dome, David's Sling, and the Arrow system are, they are just pieces of a larger puzzle. The laser weapon completes that puzzle by adding a new layer of defense that is faster, more precise, and more cost-effective than anything that has come before it. With this new powerful weapon, Israel is positioning itself as a leader in missile defense, ready to face the most advanced threats the world has ever seen. As the world gets closer to 2025, Israel's defense landscape is on the verge of a major shift. The upcoming laser weapon system is expected to be the most advanced defensive tool ever deployed, designed to take on hypersonic missiles that are impossible to stop with traditional methods. This system is part of a much broader trend in military technology, where speed, precision, and efficiency take center stage. This powerful laser weapon represents a future where lasers, not missiles, may become the first line of defense in modern warfare. A unique feature of this laser weapon is its ability to engage multiple targets quickly. When Israel faced waves of missile attacks from Iran and Hezbollah, it became clear that traditional defense systems struggled to keep up. A barrage of dozens of rockets or drones can overwhelm even the best defenses. But a laser weapon does not face the same problem. As long as the system has power, it can continue firing without the need to reload or wait between shots. This makes it a perfect response to mass missile attacks. But the real breakthrough is the system's ability to handle hypersonic missiles, which represent the next generation of missile threats. Hypersonic missiles can not only travel at incredible speeds, but they can also evade detection by flying at lower altitudes, following unpredictable flight paths. The few seconds of reaction time that other defense systems rely on are not enough when facing a missile that moves this fast. With lasers, that's not a problem. The system operates at the speed of light, ensuring that the missile is hit and destroyed before it gets anywhere near its target. Israel's enemies are not standing still either. Countries like Iran are trying to improve their missile technologies, making their weapons more accurate and harder to intercept. But Israel's decision to invest in a laser weapon system shows its commitment to staying ahead of these developments. The laser defense system will ensure that even the most advanced missile threats can be destroyed before they pose a danger to the country. The laser weapon is more than just a defensive tool. It represents a shift in how wars will be fought. Traditional missile defense systems are based on the idea of intercepting a missile after it has been launched, using another missile to collide with it mid-air. But this approach is increasingly proving to be outdated, especially against faster, more advanced threats like hypersonic missiles. Lasers, by contrast, offer a different kind of solution because they are faster, more efficient, and far more versatile. In a way, this laser weapon marks the beginning of a new era in warfare. The idea that a beam of light could stop the most advanced missile threats in existence was once the stuff of science fiction. Now it's about to become a reality. For Israel, this system could mean the difference between vulnerability and security in an increasingly dangerous world. As 2025 approaches, the stage is set for the deployment of one of the most advanced defense systems ever built. Israel's investment in the $1 billion laser weapon system is a testament to its determination to stay ahead of its enemies. The weapon's ability to engage and destroy missiles, drones, and other airborne threats with precision and speed ensures that Israel will be prepared for whatever challenges the future may bring. Nations with control over key military routes often have more power and influence, but just having a strong military base alone doesn't work anymore. Countries need to adjust their strategies for different situations, and the United States is leading the way. What new technology is helping the United States Armed Forces handle today's battles? How are they changing the way they work in the ever-evolving world of military strategies? Join us as we explore the capabilities of the United States' future war threat drones that would become a threat to Russia and China. Kratos, a company that makes drones, has become a leader in changing how air warfare is conducted. This is particularly important now because other countries are getting stronger militarily, and fighter jets which are more expensive to build and operate. The company is a leader in making drones that can be reused, and they design these drones to work together with regular aircraft in coordinated missions, even in dangerous or contested areas. Leveraging its deep knowledge and experience in creating high-performance subscale aerial targets, Kratos has designed and introduced the first attritable UAS built specifically for that purpose. These UAS offer an economical but still highly effective option for contemporary military operations. The outcome is a state-of-the-art line of tactical drones that are inventive, deployable, and high-performing. They change the equation when it comes to balancing price and performance. The XQ-58A Valkyrie combat drone is the key to Kratos' new approach. It's adaptable and delivers a lot of value on the battlefield. Its cutting-edge capabilities make it a crucial component of air power strategies going forward. The Valkyrie gives militaries an edge in staying on top in combat zones that keep getting tougher and more complex. The Valkyrie is a drone that is changing how wars are fought. It uses artificial intelligence to either team up with fighter jets or operate solo. The goal is to revolutionize modern warfare. The prototype was created after a ton of development work. Now it's a critical part of a multi-billion-dollar military effort to use artificial intelligence to get a leg up on advanced adversaries like China and Russia. It can fly up to 3,000 miles and as high as 45,000 feet. It offers a potent combination of long-range capability, high subsonic speeds, and remarkable agility, while still being highly cost-effective and able to survive in challenging environments. The aircraft's versatile mission kit configurations enable it to effortlessly take on a variety of roles. These range from conducting reconnaissance to deploying an assortment of lethal munitions using its internal bomb bay and wing stations. The Valkyrie is even more powerful because it can work in swarms. Lots of them can overwhelm enemy defenses or buddy up with regular aircraft. This swarm ability, combined with its readiness to take on near-peer adversaries, cements the Valkyrie's vital role in winning and keeping control of the skies and seas in contested areas. It shows where things are headed in terms of flexibility and usefulness for the United States Armed Forces, and takes some of the same design and manufacturing tricks Kratos used for its low-cost target drones and builds on them. The Valkyrie performs super well, but still falls in the attritable cost range. That's a category from the 2024 National Defense Authorization Act for weapons that are okay to lose in battle because they are cheap enough to replace. The Valkyrie's cost-effectiveness and cutting-edge capabilities make it a vital asset in modern combat operations and a crucial enabler of the Department of Defense's mass mission strategy. During its most recent test flight at the Eglin Air Force Base in Florida on the 20th of September, the Marine XQ-58A prototype showcased its newly integrated Link 16 capabilities. This progress represents a major step forward in collaborative combat for uncrewed aircraft systems. The test flight's preliminary findings verify that the prototype satisfied the necessary criteria, demonstrating its capacity to provide innovative solutions for next-generation warfare while remaining cost-effective and versatile. The addition of autonomous tactical information exchange through the newly incorporated Link 16 capabilities represents a crucial step forward for the Marine Air Task Force. It substantially improves their capacity to carry out integrated and joint operations. The Marines have now completed 3 successful XQ-58A Valkyrie flight tests. They are actively assessing a spectrum of possible applications for these drones, such as uncrewed electronic warfare aircraft, surveillance and reconnaissance platforms, airborne communications relays, and wingmen for crewed fighters like the F-35. With each test, the Valkyrie further exhibits its adaptability in performing vital combat and support roles. The company also recently introduced a special launch trolley that allows Valkyrie drones without built-in landing gear to function on conventional runways. This development guarantees even greater versatility and operational flexibility, reinforcing the Valkyrie's position as a foundation for future uncrewed and collaborative combat missions. This drone doesn't need a runway to work. It takes off using a fixed launcher on the ground with rocket boosters that fall away after launch and lands with parachutes when the mission is done. While this setup makes it unique, the Valkyrie remains Kratos' main combat drone and keeps getting updates. The newly announced version, featuring internal landing gear, represents a major leap in expanding Valkyrie's scale and scope of capabilities. This enhancement not only broadens its operational flexibility, but also aligns it more closely with the Air Force's interest in versatile and adaptable drone systems. The addition of landing gear paves the way for the Valkyrie to transition into more traditional launch and recovery operations, while still retaining its edge as a high-performance, cost-effective, unmanned platform. This shows how the Valkyrie keeps getting better, with Kratos making new advances in unmanned combat aerial technology. For those wondering what an unmanned combat aerial vehicle is, they are pilotless aircraft that can gather intelligence, watch areas, find targets, and carry weapons like missiles and bombs. Unlike single-use attack drones or surveillance-only drones, these aircraft are controlled by operators on the ground, can attack targets, and then fly back to base. They can work with different levels of independence, but humans still make the key decisions. Since these aircraft have no pilot in the cockpit, they don't need space or equipment for a crew. This makes them lighter and smaller than regular aircraft. Many countries now make their combat drones, while others buy them from abroad or are working on building them. Back in the year 1940, radio inventor Lee DeForest and TV engineer Sanabria first wrote about the idea of combat drones in Popular Mechanics. However, in 1971, Foster, who built model planes as a hobby, thought about using similar ideas to make weapons. By 1973, DARPA built two test drones called Prairie and Calera. These drones used a changed lawnmower engine and could fly for 2 hours while carrying 28 pounds of cargo. In 1973, during the Yom Kippur War, Israel flew unmanned Ryan Firebee drones to trick Egypt into shooting all its anti-aircraft missiles. This worked without putting any Israeli pilots at risk, and then Israel could attack Egypt's now empty defenses. Later in the late 1970s and 80s, Israel created the Scout and Pioneer drones. These new designs were lighter and more like gliders, similar to the drones we use today. In 1982, Israel changed how drones were used in war. They used them to watch enemy areas in real time, jam electronic signals, and trick radar systems. During Operation Mole Cricket, at the start of the Lebanon War, these drones helped Israel take out Syria's air defenses completely, and no Israeli pilots were lost. Israel's success with drones caught America's attention, so they went ahead and bought several drones and modeled the designs after Israeli designs. The first Persian Gulf War became known as the First Drone War. A Navy report from May 1991 noted that they kept at least one drone in the air at all times during Desert Storm. After seeing how useful drones were in this war, militaries worldwide started developing their combat drones. In recent years, the United States has used more drone strikes against targets in Pakistan and other places as part of the War on Terror. By January 2014, estimates showed 2,400 people had died from these drone strikes over 5 years. By June 2015, the total number of deaths from the United States drone strikes was thought to be over 6,000. In 2020, Turkey made history by being the first country to use combat drones in a large, organized attack during regular warfare when they struck forces in Syria. The drones hit enemy locations, protected ground troops, and helped direct artillery fire. That same year, both sides used many drones during the fighting between Azerbaijan and Armenia in Nagorno-Karabakh. In 2022, TB2 drones played a key role in defeating Armenian forces. Drones were also used heavily when Russia invaded Ukraine in 2022. They give a big cost advantage in war. People can take basic drones that cost $2,000 at stores like JB Hi-Fi, add a grenade, and use them to destroy enemy equipment worth $5 million. For instance, the TAI Aksungur was built by Turkish Aerospace Industries for Turkey's military, and it was built on technology from TAI's Anka drone series. The drone is able to carry different equipment depending on the mission. It was also designed for long surveillance flights, gathering intelligence signals, watching sea areas, or combat missions. Right now, the Baker Kizilelma is a combat drone being developed for Turkey's Air Force and Navy. It's being made by Baykar, the same company known for the TB2 drone. This new drone will use a jet engine, can take off from aircraft carriers, is hard to detect, and can fly faster than sound. On March 2022, Baykar's Chief Technology Officer, Selçuk Bayraktar, announced they had started building the first test version. The Tyanka 3 is a new combat drone being developed by TAI. It uses a single engine and has a wing-shaped body design that helps make it hard to detect. Its main jobs will be taking out enemy air defenses, flying deep into enemy territory, and bombing targets. The Taranis is Britain's test program for combat drone technology. It is part of their Strategic Unmanned Air Vehicle Experiment program. BAE says the Taranis project costs £124 million and would run for 4 years. The goal is to create a demonstration combat drone that can operate on its own without being detected. The Taranis drone can take off weighing about 8,000 kilograms and is about as big as a BAE Hawk, making it one of the biggest drones in the world. It is designed to be stealthy and fast and carry weapons to hit multiple targets. It can also defend itself against both manned aircraft and other drones. Work on building it started in September 2007, with ground testing beginning in early 2009. It made its first flight in August 2013 in Woomera, Australia. One way the United States military is staying ahead of the curve is the Joint Unmanned Combat Air Systems, which was a project shared by the Navy and Air Force to develop combat drones. DARPA ran the program, but it was shut down in 2006. The program planned to create drones that were almost invisible and would carry precise weapons like the Joint Direct Attack Munition or small-diameter bombs to take out enemy air defenses. Operators would have used up-to-date information from sources like satellites to plan and adjust to battlefield changes. The program later came back to life as UCAS-D, a Navy project to create drones that could take off and land on aircraft carriers. UCAS-D and the Northrop Grumman X-47B became the Navy's new drone programs after JUCAS ended 2006. Boeing is also developing its carrier drone called the X-45N. In a New Year's 28th editorial called China's Naval Ambitions, the New York Times suggested that the Pentagon should help the United States naval forces in Asia work from farther away to avoid Chinese missiles. They said stopping orders of the DDG-1000 destroyer was good because its missile defense wasn't strong enough. They also recommended using fewer short-range crewed aircraft like the F-18 and F-35, and instead using more carrier-launched combat drones. The Air Force changed its combat drone program from shorter-range attack aircraft to long-range bomber drones. These included the Scaled Composites Model 395, the Scaled Composites Model 396, the General Atomics MQ-9 Reaper, first called the Predator B, the Aurora Flight Sciences, Israel Aircraft Industries Eagle, Heron 2, and a Lockheed Martin model that wasn't named publicly. The technology for their long-range strike program comes from the Lockheed Martin Polecat test drone. The E-8 Surveyor is still in the early testing stages. It will be a jet-powered drone with fixed wings meant to replace the CL-289. E-AIDS is testing a prototype called the Carapace, which is a modified Italian Mirage 100 drone. When finished, the Surveyor will be hard to detect, fly up to 850 kilometers per hour, 530 miles per hour, stay in the air for up to 3 hours, and carry advanced sensors, including signal intelligence equipment. It will also be able to carry and drop sensors or small weapons. In the mid-20s, ISIS started putting explosives on regular commercial drones like the Chinese-made DJI Phantom to attack military targets in Iraq and Syria. During the Battle of Mosul in 2016 and 17, ISIS used drones to watch enemy forces and drop grenades and other explosives using makeshift holders. The British Royal Air Force bombed one of ISIS's drone facilities during this battle. During the Syrian civil war, militant groups also used drones to attack, like in early January 2018, when they sent a group of bomb-carrying drones to strike Russian bases in western Syria. In the 2020s, Mexican drug cartels started using drones to drop hundreds of bombs on both police and rival gangs during territory fights. During the Russia-Ukraine war, drones have been used a lot. Ukrainian soldiers use GPS to guide drones to find Russian artillery and help direct their artillery strikes. When these GPS signals get jammed, drones have to follow preset paths through jammed areas until they can connect again. Some Western-supplied drones, like the AeroVironment Switchblade, can find targets on their own, but need a human to approve any attack. In October 2022, a video showed 2 drones crashing into each other, with one becoming unflyable. People said the drone that recorded the video was Ukrainian and the destroyed one was Russian. If true, this would be the first recorded fight between two drones. On December 27, 2022, North Korea flew 5 drones into South Korea with one reaching Seoul. All 5 made it back to North Korea despite being chased for 5 hours by fighter jets and attack helicopters that fired about 100 rounds at them. During this, a South Korean KT-1 Wongbee crashed, though both crew members survived. South Korea's military leaders said they could stop attack drones, but had trouble dealing with smaller spy drones. A top official, Kang Shin-chul, admitted their military wasn't prepared enough, which worried many people. He said they needed to use better detection equipment to spot enemy drones early and have more ways to shoot them down. South Korea's President Yoon Suk-yeol said they would invest in stealth drones that could fly into North Korea and create a new military unit for them. South Korea's defense ministry announced they would spend $560 billion over 5 years on 4 new ways to fight drones. They'll use an airborne laser to destroy bigger drones while using jammers for smaller ones. They're also making a special anti-drone unit with 2 squadrons and are already testing the laser and expect it to be ready by 2027. The jamming system is called a soft kill method. In March 2009, The Guardian reported claims that Israeli missile-equipped drones injured 48 Palestinian civilians in Gaza, including 2 young children in a field and several women and girls walking on an empty street. Later in June, Human Rights Watch looked into 6 drone attacks that reportedly neutralized civilians. They said Israeli forces either didn't take enough care to make sure their targets were fighters or didn't properly tell the difference between fighters and civilians. In the United States drone program, civilian deaths still happen, though some officials like John O'Brien say drones lower the chances of civilian casualties, and even though drones can watch areas closely and get instant information, they can still make mistakes. The United States drone strikes have been reported to also hit civilians by accident. One example happened in February 2010 near Khod in Uruzgan province, Afghanistan. More than 10 civilians in 3 vehicles driving from Daikundi province were claimed to be injured when drone operators wrongly thought they were enemies. Between 2004 and 2010, a report by PakistanBodyCount.org counted 1,065 civilian casualties from drone strikes. Although these claims have not been proven, insiders see these claims as propaganda to make the public turn against the United States. Drones have become an incredibly powerful asset for the United States military. They give their armed forces a huge leg up in all sorts of situations. The technology is only getting better as artificial intelligence helps drones become smarter and more capable. Sure, there are risks, like the potential for civilian casualties, but the military is putting more and more precautions in place to avoid harming innocents. They know drones are here to stay, so they are focused on using them responsibly. At the end of the day, drones are a total game changer. They allow the military to project power without putting boots on the ground. And as AI gets more advanced, drones will be able to do even more to keep the public safe. It is a brave new world out there, and drones are going to play a big part in it. The United States military knows this and is making sure they stay ahead of the curve. Drones aren't going anywhere. In fact, they are only going to become more important as the technology improves. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.